Okay, so first of all, thanks for the invitation. I'll be talking about a very recent work with Jacopo De Nardis and Takato Yoshimura about diffusion from convection. So let me just start by introducing very basic notions of transport and different transport universality classes we can have. So first of all, why are we interested in transport and in particular in transport associated with conservation laws? Well, because if we don't have any conservation laws, usually the dynamics is quite boring in a sense that everything like all correlation functions and stuff like that dies off very quickly. But if we have some systems such as Hamiltonian systems or systems with translational invariance, we have some local conservation laws. To local conservation laws, a set of currents is associated through the continuity equation. So I'll focus on one-dimensional systems. I'll mostly talk about lattice systems, but basically the procedure can be also used for continuous systems. So what happens if you have some local conserved quantities in your systems is that local observables develop hydrodynamical tails, so time scales become relatively long, and we can observe some interesting physics. So let's say that I have my one-dimensional chain, and I couple it at the ends to some leads, which pump in some energy or spin or charge from one side, and I take it out on the other side of the chain. Then depending on the type of the system, different things can happen. So what we usually expect if my charge carriers are kind of scattering randomly with some environment is that Fourier or Fick's law holds, which just tells me that our current or my current is proportional to the gradient of the charge. And this corresponds to the ordinary diffusive transport. So if we go back and really consider our system with the leads, this tells us that if we keep the difference of potentials on two different size constant and increase the system size, the current will decay proportion 1 over the system size. So what can also happen if we have, let's say, conservation of momenta or some non-trivial conservation laws is that the current will not depend asymptotically on the system size. So no matter how big your system is, there will be finite amount of current flowing through the system if you introduce the finite difference of chemical potential. And this is naturally associated to conservation laws because it basically tells you that also a part of the current is conserved. Finally, we can have some anomalous behavior. So the current will not scale as 1 over the system size, but rather with some non-trivial exponent. And in particular, this is connected to super diffusion. And such behavior, for those who know of it, occurs in KPZ or KPZ equation. So the anomalous behavior. Sorry? Also for everyone else, no problem. Okay, so let's be a bit more quantitative. So how do we probe different types of behavior? We do standard Kubo linear response approach. So basically we take our Hamiltonian, which is the dynamics which we want to probe. We introduce a gradient of charge corresponding, well, with an appropriate field associated with the charge. And then we look at how the system responds if this field is very small. So basically what we're interested in is the behavior of currents of charge L if we introduce small gradient of charge Q in the system. In this case, using continuity equation, we can simply derive the Kubo formula. So here what we're looking at is basically if we introduce this constant gradient of charge, we're interested in how the current in the system will increase on average. Why does it increase? Well, even if this gradient is small, well, even if the prefactor is small, the charge at the ends will be like the difference of the charges which are for the spaces which are very far apart will be infinite. So this will induce current which will increase linearly with time in our system. So that's why we put here factor 1 over t. And in fact, this just defines our Drude matrix, which is connected to connected correlator, time integrated and space integrated connected correlation function. Well, to be completely honest, this should be a Kubo-Mori inner product, but later on we'll be dealing only with conserved charges, so one can show that up to some small corrections, this actually reduces to the connected correlation function. So this tells us what is the rate of the increase of the current in our system. Then we can also be interested in corrections to this rate of increase. And this is given by the Onsager matrix, which is basically just current, which you expect in a system after infinite time if we subtract this linear ramp. So this is just a correction, and one can, again, using just linear response, derive this expression for the Onsager matrix. Okay, what does this tell us? So here we have currents associated to different charges. We introduce gradient of some charge. We are interested in well, how the currents of charge L will increase if we have currents of charge K. And this gives us the Drude matrix. If we diagonalize this matrix, the information we get is the following. Let's say that we have just two charges and a particular form of Drude matrix. So then we can diagonalize this matrix, and what it will tell us is the following. So if we take initially some homogeneous state, let's say some finite temperature or infinite temperature density matrix, and then create a perturbation at center, the eigenvalues of Drude matrix will tell us how excitations will propagate in this system, in particular, how fast the excitations will be. So this is just a plot for the setup I described at different times. So what we see is basically that we have two excitations because we have two charges which are moving with some constant velocity, and this velocity is given by the eigenvalues of the Drude matrix. But what we also see is that this excitation spread as time increases, and the width of this spread is characterized by Onsager matrix. Okay, so this is a physical picture. So here is another interpretation of Onsager matrix and Drude matrix. In particular, if we look at the expectation value of the current in a background which is slightly varying, we can expand it in power series. So the first term is just proportional to some conservation laws. So current is proportional to some conservation laws in some slightly varying state, which means that part of the current will be conserved. So if dLk is non-zero, this means that part of the current is conserved. We have ideal transport and so on. But then we can go to the next order, do the gradient expansion. And by definition, here we have Drude matrix. Diffusion matrix. Because if we put this expression in continuity equation, the second term just produces the diffusion equation. Okay, but now we can actually connect the diffusion matrix to the Onsager matrix. And this is just an Einstein relation. So this is conductivity, this is diffusion, and this is susceptibility. Of course, now we have many charges, so we have to sum, so multiply matrices. But in principle, if there is only one charge, this just tells us conductivity is equal to diffusion times susceptibility. Okay, the important point is that diffusion constant and Onsager matrix depend on conservation laws. And yeah, it's a matrix. So if we have n conservation laws, it's n times n matrix. And yeah, I mean, we sum over the repeated indices. So this is actually, we can calculate the diffusion matrix. The elements are djk, and we have C, which is again a matrix. Then what this equation tells you that L is just times C. Just an Einstein summation convention. Okay, so the Onsager matrix is expected to depend on expectation values of conservation laws. So in particular, expectation values of conservation laws of a state around which we are perturbing. So as I said, so here we have weakly inhomogeneous state. That's why we do this expansion. And in particular, what I'll do here is show what kind of contributions to diffusion constant Onsager matrix arise due to the existence of convective or ballistic modes, so some conserved charge densities. So this contribution to Onsager matrix I'll denote by LC as for convective. Yeah. Yes, yeah, okay. So let me introduce just some notation and basically things we need. So what we do is, I would say, quite naive version of hydrodynamical assumption. So the basic idea of hydrodynamical assumption is just to try to identify some degrees of freedom which are long-lived. So what we do is basically take our lattice, coarse grain it. So we divide it into chunks of length L. So each, we have in principle an infinite lattice. We can imagine that there is infinite number of spins. Then we just cut it into parts of lengths. Delta X is L. And then we define operators which are averaged over this, so over this lattice, or over this sublattice. So you can see that basically here we are summing, if we're at some position X, we sum to minus L half, from minus L half to L half, the operators, which should be quasi-local, which means that in principle, these operators can also be based in the neighboring cells, but because they're quasi-local, their contributions, which come from neighboring cells, are really small. I'll be a bit more quantitative later on. So hydrodynamical assumption is basically that locally your system equilibrates. So how do we understand this? Well, we have a set of equilibrium states, which depends on a set of chemical potentials. So let's say Qi are my conservation laws, local conservation laws. So then, in general, we expect that equilibrium states is described by generalized Gibbs ensemble. Once again, we use summation conventions. But okay, if we now say we expect each cell to equilibrate, then we just write these ansatz for the density matrix. So we introduce X dependence of chemical potentials. And here what is meant is actually summation over X by the steps of delta X. Basically, this is just a density matrix which involves chemical potentials which are site dependent. Sorry? OI are all the same. Yeah, I mean, if we have, yeah. So they are all the same. It's a sum of the same operators over one. Yeah. Exactly. No, Qi is actually sum over all Qi, so throughout your system. OX? Oh, this is a bit different than this one. The I is a site index, but it doesn't mean that this is necessarily an operator at a single site. What it means is that it's an operator which starts at site I. And then it... yeah, exactly. X just tells you where the middle of the cell in your chain is. Sorry? Yeah, Q, capital Q. Q, this? So, I mean, Qi is sum of local operators. So O, let's say large O is just the sum of OI over all I. And then, but no, so, okay, let's say Q. Q is equal to sum over I Qi, but then we can divide this sum into different cells. This is the site index. Okay, yeah, no. The large things describe the operators that are like throughout the lattice, if you want, not just in single hydrodynamical cell, not at just one side, but you take a single site operator and you sum it over whole lattice. For different, sorry for the confusion. Yeah. Exactly. Well, yeah, I, X, whatever. Yeah, okay. Sorry? This Qi of X. Yeah, Qi are conservation laws. They label conservation laws. Yeah, if it's large, it's throughout the system. If it's small and this math frac, it's in hydrodynamical cell. If it's small, ordinary, it's just on an ordinary lattice. Okay. Okay, so what we'll need is basically how the connected correlation functions behave if we assume that our Qs are composed of quasi-local operators. And we can define connected correlation function simply as the nth derivative of expectation value of O in some state rho. So here there is a state rho which depends on x1 to xn and beta 1 to beta n. So it depends on beta 1 to beta n, but it also, because it's slightly inhomogeneous, it's only thermalized locally, we still keep the site indices. And in the end, we take a homogeneous limit. So we set all of the beta I x j to beta I. And one can show that basically an endpoint connected correlation function gives you something which is finite and is placed in the same hydrodynamical cell. So for instance, if we have here x1 not equal to x, then this will give us 0, and we'll only get the contributions which are constant, maximally constant, because there is L here. But if we have overlapping of all operators in a single hydrodynamical cell, we get something that is proportional to the volume of this cell. And this is basically just, well, we're summing, it's easy to understand. I mean, even forget about correlation functions. So expectation value of some local observable will in general increase linearly with the number, with the size of the cell. And then this comes from just the boundaries of two cells. So because, well, you can have corrections from the boundaries because the operators can slightly overlap. Okay, so that's basically what I say. So they are extensive within the hydrodynamical cell, and corrections arise due to the boundaries. Another concept that's quite useful is notion of normal modes. So if you remember the picture I showed you, normal modes are excitations which are on Euler scale, just behaving as some localized peaks which are moving with constant velocities. And we can obtain normal mode simply by diagonalizing Drude weight matrix, and their speeds, as I mentioned before, are also obtained as eigenvalues, and this rotation from the basic charges to normal modes is obtained by diagonalizing Drude weight matrix. So all this can be done, and then one can see that on top of some thermal states, normal modes are localized on Euler scale. So they're all moving with well-defined velocity. So this is just a continuity equation in K-space. And this just tells us that there are excitations traveling with velocity vi. Yes. So Qi are just hydrodynamical densities within the hydrodynamical lattice, and they and J, so normal modes, are just a linear transformation. So you have many Qis, but if you look at a certain Qi, you will see many peaks emerging, like the thing I showed you before. Okay, let's say I have two Qis. In general, if I look at the two-point function of one of them, I'll see both of the peaks. So, or if I have n modes, I'll just see n modes appearing in this correlation function. And the idea of normal modes is just to separate them. So when you look at two-point function at one normal mode, you'll just see one peak propagating with well-defined velocity and spreading some coefficient given by the Onsager matrix. So okay, these are the normal modes. And I'll actually use this equation. I'll try to argue why I can use it. I'll use this equation not only on the level of two-point correlation functions, So if I just have two operators here, but also, okay. Also on the level of higher point correlation functions with respect to the same density matrix. Okay. So what I do basically is I do something that I call a hydrodynamical expansion. So this is a conjecture that on level of correlation functions, I can expand my current at some place x sine t in terms of variations of conserved quantities. So I can expand it to all levels. And basically the physical picture of this is that when you apply a current to density matrix in some hydrodynamical cell, it creates a lot of excitations. But the ones that will survive, well, after we do appropriate procedure, are conservation loss, densities of conservation loss, just because of what I told you before. So they are just propagations that will always propagate, so they will never decay. Approaches. Okay, the other view of this is basically that I'm expanding my density matrix in terms of fluctuations of my conservation loss. And I can do that to calculate the Drude weight. So I define, well, I just write my Drude weight in terms of hydrodynamical currents. And basically this corresponds to applying this expansion to expectation value of current JL. And this gives me the well-known result. So Drude weight can be actually expressed as a projection of a current, so J, to charges QL. Yeah. Okay. J. Yeah. JKL. U I J. JL. Then U I J to -1. And this, once again, you have to consider as a matrix. So this is an inverse of a matrix. It's not just a number to -1. So that's what's written here. And basically, this follows also from the idea of hydrodynamical projection, where you just say, well, what survives in long time limit are just some conserved quantities. So I have to express this JK in terms of conservation loss. Okay, and there is I mean, this normal mode basis is quite nice because in this basis, the Drude weight simply reads as follows. So it's just a 2-point correlation functions, and there is no, so this C normal mode basis is, one can show that it's actually diagonal. So this is the result in a normal mode basis. Okay, so now we can try to obtain the Onsager matrix using the same expansion. Okay, I forgot to mention that you plug in higher orders into this expansion. When you take L, small l to infinity, they will all vanish. So you'll only get this contribution from the first order of this expansion. If you plug this in, you'll see that you get a contribution which scales as 1 over L. If you plug higher order terms, it's even worse. So they get more and more suppressed. Okay, so for the Onsager matrix. So basically, what you get here is endpoint correlation function, well, two-point correlation function, which, as I mentioned, scales linearly with the size of the cell. When you're going, what you're doing here is taking derivatives with respect to expectation values, which are extensive. So basically, this produces order L, and these two derivatives produce 1 over L squared. So that's why they vanish, and the higher order terms vanish even worse. But okay, the second order terms vanish in the expression of Drude weight. But if we calculate the diffusion constant, we see that the first order term actually cancels out. Well, this is just because, well, on Zagar matrix, it's just because we are subtracting the Drude weight. So basically, we're subtracting the first order contribution. And what you're left with is just the second order in our expansion. And in particular, in the normal mode basis, it takes this very simple form. So it's just a three-point correlation, connected correlation function of currents and normal modes divided by velocity difference of the normal modes. So how can one understand this? Basically, we can view current at point 0 as creating some excitations at point 0, and these excitations are traveling through the lattice, and when they hit the different lattice cell, they give a contribution. But both excitations, so because it's a second order, so both terms have to hit the lattice cell simultaneously in order to give a finite lattice cell where the current is located, another current. Okay, be a bit clearer. So this current just creates excitations on top of density matrix. And this current just sits at some point. And we can take time to excitations, so time dependence to excitations that this current created. So we have just some normal modes which are propagating with constant velocities. And because connected correlator will vanish whenever the three terms are not all three, so J and 2Qs are not simultaneously in the same cell, we just get the contributions when, well, all of the three of the terms are in the same cell. But the time that all three terms will be in the same cell is actually inversely proportional to the difference of the velocities of the modes, because if one mode is slower than the other one, so the other one will already leave one cell and the first one will be left behind. So that's how 1 over the difference of velocity proportionality constants comes from. And this overlap is just an overlap which comes from overlapping of current and the two normal modes in the same cell. Okay, are there any questions? I lost everyone? Or, huh? Not lost, okay. But what? Okay. Sorry? Gain, perfect, that's very good. So let me try to relay this result to some previous, let's say, more rigorous approaches, which were actually the inspiration for taking such an expansion. So the first one was lower bound by Tomasz Prosin in 2014 in terms of quadratically extensive quantities, and what Tomasz proved is basically that on-Zagar matrix can be bounded with the expression like this, where Q is now not linearly extensive, so it's not expectation value of Q in some general state is not proportional to L, but it's rather proportional to L squared. So basically using a Lieb-Robinson theorem and quasi-locality and exponential clustering, Tomáš proved that Onsager matrix can be lower bounded by the overlap of J with this quadratically extensive conservation law squared divided by the norm of this quadratically extensive conservation law with some constants which are, okay, so I have 5 minutes. Okay, well, I'll finish quickly. So basically what you can see here is that this scales as L squared, but also our guy here scales as L squared, and there is square of this term here. And here we have some velocities, it's the difference of some velocities, and actually we can reproduce up to the factor 4 the previous bound just by proving some property of normal modes and inserting an upper bound for the an upper bound for the difference of velocities, which is given by Lieb-Robinson velocity. So we can show that this actually, this actually is equivalent as this bound if we do this manipulation up to the factor 4, which can be amended for because Tomáš was considering actually the quantities which were conserved up to the things on boundaries, so up to the boundary contributions. So there is another lower bound, which is lower bound in terms of the Drude weight curvature. Once again, we can see that our expression, if we take here a maximal difference of two velocities in all term, actually reduces to this exact lower bound. Okay, our result, so this convective contribution, we can show that it actually is equivalent to exact Onsager matrix in classical and quantum integrable systems. So it accounts for the complete contribution to, it gives a complete contribution to diffusion in integrable systems. It also relates to nonlinear fluctuating hydrodynamics and basically KPZ physics. So nonlinear fluctuating hydrodynamics is a theory by Herbert Spohn, which basically says that if you have some conservation laws, let's say you have current and you have a single conservation law, and if square of this conservation law couples to the current itself, it predicts infinite diffusion constant, it predicts different universality class corresponding to dynamical exponent 2/3. And actually we can see that we also get divergence of diffusion constant provided that, well, normal modes have an overlap with our current, and if there is a degeneracy of velocities. And if, of course, if we have self-coupling, so this is something he calls self-coupling, this means that Ni is equal to Nj, so I is equal to J, which means that we have degeneracy, and we immediately get the divergence of diffusion constant. Okay. Outlook. So the question is, what are some of the other contributions to diffusion? Well, judging by Tomáš's lower bound, there can be some quadratically extensive quantities which are independent of squares of linearly extensive ones, basically the contribution we described. Okay, one thing that is missing is a more formal treatment, and I would like to refer to Benjamin's future publication, where he provides a more formal view on our result. Okay, there is also a problem. So in integrable systems, we can compute diffusion matrix Drude weights. What we are still unable to obtain is super diffusion constant. So in case we have integrable systems with some abelian symmetries, one can show that diffusion constant diverges, but not in a way that it would be ballistic, but in KPZ kind of a way. And we're still unable to obtain diffusion constant for the super diffusive behavior. Okay, it seems that our approach implies that one could apply and obtain contributions from convective modes also to for higher cumulants of the currents. And finally, it would be nice to understand if there is such a contribution also in dimensions which are higher than 1. Okay, thank you.
Okay, so one or two comments.
Back to the previous slide, just the last one. To your second point, no symmetry restrictions. This is not quite the case. You can get diffusion, I mean, just normal diffusion without any particular symmetry. It's a question of choice of parameters. You can fine-tune parameters such that you get diffusion. Don't need a symmetry, that's what I'm saying.
Sorry?
You do not need a symmetry to get diffusion.
Yeah. What do you mean? I mean,
in your second point, you say you get super diffusion if there's no symmetry restriction. But you can have no symmetry.
No. Okay. What I mean is no symmetry restriction is very specific. So usually you can argue that there are no off-diagonal terms in this matrix, which cause in this G matrix, if you have some symmetry restrictions, such as parity invariance. So let's say what usually happens is you have some conservation law which is translationally invariant and invariant under parity. Then you can, I mean, show just by a continuity equation if your dynamics is parity invariant, so if you're Hamiltonian, that the J will be, current will flip, right?
What I'm saying is that you need a symmetry to get diffusion.
No, but I'm not saying this is super diffusion.
Yeah, but you say if you have no symmetry restriction, then you will get super diffusion.
No.
This is what's written there.
I mean, okay, is it clear what I mean?
No. What I'm saying is that even without any symmetry, you can just have diffusion. You don't need any symmetry.
Yeah, sure. I mean, this can still be 0.
Yeah. This is the point. You claim that you need.
So you can still take a special example where this will vanish. Of course, it's not.
No, what I'm saying is that whether you get super diffusion or not has nothing to do with symmetries. That's what I'm saying.
Well, you can argue that you will not. You don't expect it because of symmetries.
Hey, if there's a symmetry, you may expect special properties, but without symmetry, anything can happen. That's what I'm saying. Just the question of choice of parameters.
If this term is non-zero, then you'll get super diffusion.
Sure. But whether this is non-zero or not is not related to symmetries. It's related to parameters.
I mean, usually.
No, it's not the case.
I mean,
No, look, I know this. I've done the calculation myself, right? I can give you
it's time,
example. Just go to this paper.
Maybe you can discuss later.
Yeah.
So why would this term vanish if not for the symmetries?
Because you can choose parameters such that it becomes 0. And I can give you explicit examples. It's actually in the paper, in this volume that you cite. The preceding paper is by myself and Slava Popkov, and there's an explicit example where you get diffusion without any symmetry.
Anyway, it's time, so let me go to the next speaker. So let's thank speaker again.